Hello, today we will be presenting our orbital mechanics project. In order, we are Tyler Lyman, team lead,
Nicholas Tercios, deputy.
Wyatt Raby,
Andrew Moffat,
Chase Edwards,
Gavin Maher.
and today we will be talking about our orbital trajectory, Project Nomad. The goal of this mission is to reach the ISM point, of which the spacecraft will use the sun as a solar lens to take refined images of the TRAPPIST solar system that is light years away. The ISM point is 550 astronomical units away, well outside our solar system. We must depart between the years 2035 and 2050 and arrive at the ISM point as quickly as possible. The secondary objectives of our mission include using flybys to reduce fuel mass.
when comparing the TRAPPIST and Wolf system, we came to the conclusion that we would go to the TRAPPIST ISM point. The TRAPPIST and Wolf ISM points are both 550 AU away, making them similar in time of flight and fuel costs. While the Wolf system has a planet in the habitable zone, the TRAPPIST system has 3 planets residing there, giving it more potential to forward our search for interesting exoplanets and life.
The application of Lambert's problem determines an orbital transfer through the use of 2 orbital position vectors and the time of flight. This is applied to rendezvous transfers between the solar bodies in order to calculate the trajectory of Nomad over its journey to the ISM point. Through the application of Lambert's problem, Nomad can achieve higher rates than the Hohmann transfer method, allowing for a shortened travel time to the ISM point. Once Nomad reaches its final transfer point, Lambert can again be applied to the position vector of the ISM point in order to reach the point of observation for the TRAPPIST star system.
Finding appropriate departure and arrival dates could be difficult without use of contour porkchop plots. These plots are generated using a MATLAB script, which takes from the FRMS the location of planets on those respective days, and then it solves the Lambert problem repeatedly for a variety of times of flights. And it produces the contour plot shown.
Based on the porkchop plots, we were able to determine that an Earth to Venus to Jupiter mission would be best to go to the ISM point. We would perform a flyby at Venus in order to rendezvous with Jupiter, since it requires more energy to go straight to Jupiter rather than rendezvousing with Venus. Furthermore, when we go to Jupiter, it gives us the largest delta V boost that we can have in our solar system, and it is essential to this mission. Things that we considered were a Mars flyby since we were going to Jupiter. However, we decided that the path deviation was not worth the energy that it would cost.
The assumptions that were used when designing the mission were all spacecraft design related. Our engines would have perfect orientation, guidance, and burn time. Additionally, the throttle control and engine ignition were assumed to be instant. Finally, 1,000 kilograms of initial mass would account for control systems, structure, power, and more.
to calculate the total delta V of a mission, we need to account for the cost of an initial departure burn, Lambert transfers, and orbital flybys. By creating MATLAB scripts for each step, the delta V values can be summed to find the total energy needed for the chosen mission. The first step is finding the delta V required to depart from Earth, which can be solved by finding the exit velocity from a Lambert transfer, and then taking out the velocity of the parked orbit. Then, by using a flyby function, the orbit after passing by the first planet can be solved for. The Lambert function is then called again from our new position to the next planet, and our post-flyby velocity is compared to the calculated Lambert velocity. This process can be repeated for as many times and as many planets in any order until we arrive at the ISM point.
The first orbital maneuver we did after escaping Earth was the Venus flyby. The Venus flyby gave us a high delta V gain of 15.3 kilometers per second, a moderate turn angle of 25 degrees, and a radius of perigee of 943 kilometers. Once we escaped Venus, we did a Jupiter flyby. The Jupiter flyby gave us a high delta V gain of 21.2 kilometers per second, a moderate turn angle of 22 degrees, at a radius of perigee of 15,424 kilometers.
The final trajectory that was chosen was a departure from Earth on January 24, 2044. A delta V of 5.929 kilometers per second is used to then get to Venus. We're going to arrive at Venus 126 days later for our flyby. A delta V is gained of 15.3 kilometers per second. We then use a delta V of 13.539 kilometers per second to go to Jupiter. We're going to arrive at Jupiter 1,300 days later for our next flyby. We're going to gain a delta V of 21.2 kilometers per second and then use 27.3 kilometers per second delta V to go to our ISM point. For our whole mission, the total mission time is 29,426 days, which is roughly 80 years and 226 days. Our departure date is January 24th, 2044. Our arrival date at the very end is August 15th, 2124. Our trajectory and total delta V is 8.127 kilometers per second, and the energy of our spacecraft, the C3, is 35.153 kilometers squared over second squared.
Based off the orbital energy required for our first leg, we conducted a trade study for the launch vehicles. It came down to the Delta IV and the Falcon Heavy. The Falcon Heavy was the clear winner due to the fact that there was no economic incentive to fulfill. A trade study was also conducted for the payload engine. The winner was the high-thrust RL-10C with a delta V of 8.88 kilometers per second.
Before I begin going over our Free Flyer program orbits, I would like to make note that an error occurred. The Free Flyer program was unable to account for the initial orbital positions of the craft and caused error in the orbits created through Free Flyer. This only had an effect on our Free Flyer images, not on the calculations used to find our data. Free Flyer is a modeling software used to model spacecraft trajectories in the solar system. The Lambert problem was inputted into the program to display the path for our spaceship and the entirety of its journey throughout the solar system to the ISM point. For our transfer between Earth and Venus, starting on January 21st, 2040, the time of flight was 126 days. For the transfer between Venus and Jupiter, starting on May 26, 2044, the time of flight was 1,300 days. Finally, the transfer between Jupiter and the ISM point had an arrival date of August 15th, 2124, with a time of flight of 28,000 days.
In summary, in order to get to the ISM point, we would be departing Earth on January 24th, 2044, and arriving at the ISM point on August 15th, 2124, for a total mission time of 80 years, 226 days. This burn would cost a total of 8.127 kilometers per second, the energy of the spacecraft being 35.153 kilometers squared per second squared. The trajectory in total would be flying from Earth to Venus and getting a flyby from Jupiter to the ISM point. And our engine chosen is the RL-10C with fuel consumption of 6,380 kilograms. These backup slides will provide the additional calculations that we used during our mission design.